one can look at the specific capacitance with respect to concentration and find out what should be the optimum concentration of the electrolyte chosen. And then how do we determine the cell operating voltage? So this is again by looking at the electrochemical voltage window, that which electrode has positive potential and which has negative with respect to the normal hydrogen electrode. And with respect to standard electrode potential, you can find out whether the electrode will be operable in the positive range or the negative range, and accordingly choose your electrodes. So I am talking of electrode material selection for positive, which one should be cathode material and which one should be negative anode material based on the electrode potential. Here is an interesting table of all the electrolytes. Probably it's not very visible, but I can go through it. So you see a scale here, this is from +3 to -3, and these are all aqueous electrolytes. On the top is H2SO4, then buffer, NaOH, H2SO4, different concentration, then KCl, NaOH. So what you are seeing basically here is the electrochemical stability range. So you can see for H2SO4 you can have +1 to 0, and then for basic solutions you can have +0.6 to -0.2. So these are the kind of typical ranges these electrolytes can withstand without undergoing any decomposition. So this is a CV curve, and here you can see the stability range of each individual electrolyte. Whereas if we move from aqueous to organic electrolytes, now what do you observe? That the electrochemical voltage window is increased. Okay, so when we have organic electrolytes, they undergo decomposition at a much higher voltage, so you have much broader voltage window. And when you have a CV curve, if you see a peaking of the voltage of the current here, that means the electrolyte is undergoing a Faradic decomposition. So this decides what voltage we should use, and electrolyte can be operated. So we can see here that for aqueous and organic electrolyte, this voltage window is limited maximum to 2 volts or 2.5 volts at best. Now how do we go higher in voltage? That is by using ionic liquids, as has been discussed little bit in the previous lectures as well. So ionic liquid is a very interesting system. They are liquid at room temperature, they have low boiling point, high polarity, moderate viscosity, and then thermal and chemical stability also is very good. And these are some of the important properties which are required for the selection of electrolyte. Now there are 3 types of system one can look at in ionic liquids. The best one for assembling a battery or a supercapacitor is the aprotic ionic liquid, where you don't have any immobile hydrogen ion into the solution, because if it is there, then you will again have problems with decomposition of electrolyte, and that will limit the voltage window. Even most of the devices with ionic liquid are assembled in glove box to avoid any moisture, because of the same reason, because you will have problems with the decomposition of electrolyte. One can make solid state electrolytes using these ionic liquids. One can cross-link them inside the polymer in situ, and that way one can have ionic liquids immobilized in the polymer matrix. And usual polymers which are chosen are like PMMA, PEO, polyethylene oxide. These are kind of polymers which can dissolve the ionic liquid, and it also encapsulates them from aerial oxidation. So once you have ionic liquid dispersed in these kind of polymers, you can use them outside the glove box. So that's the advantage. So making these kind of self-standing films